Hi, my name is Keerti Lakshminarayan, and I'm here with Alok Tiagi. We both belong to the host networking team within the wider network platform team here at NATless. We are here today to present a novel approach in trying to do a network connection between an IPv6 address to an IPv4 address without using network address translation. So let's see how that happens. We'll look at a motivation on why we need to do this. So Netflix uses hundreds of thousands of instances of AWS EC2. And the way we've architected our network is to allow for full mesh connectivity. That means every instance can access every other instance. This makes it simpler to reason and maintain. But in enabling this, we have begun to test the scaling limits of AWS. And the reason this happens is for as we grow the number of subscribers and we create more personalizations and we use more compute, each one of those compute instances or nodes uses network addresses which need to be maintained in the underlay of AWS. So AWS has some innate limits on how much it can maintain, how much state it can maintain across its entire underlay. So there are alternatives to using a flat IPv4 network, but that again increases the way we have to reason out and maintain these different network subnets or segments. So in our broader push, even though we might be able to achieve some kind of limited effect in terms of using different kinds of subnetting and segmentation, as we grow, we will eventually start hitting those limits beyond which AWS might or might not scale. So we have begun a broad push in Netflix to move towards IPv6 since early last year. So one of the things that is suggested is to also dual stack our instances to have both IPv4 and IPv6 instances, in which case you might not require a network address translation. But as you said earlier, the problem that we were trying to alleviate was to avoid having too much of network state in AWS. Now, if we dual stack each one of our instances with an IPv4 and an IPv6 address, that would create more state for the AWS to handle, and we'd be back to square one very quickly. So the idea is to move to IPv6 transparently. Here, we present a chart with our current breakdown of IPv6 traffic with IPv4. So in the past few months, we see that we've been making moderate amounts of progress towards having a larger number of IPv6 footprint. We want to make this all red. That is, we want to have complete IPv6 to IPv6 traffic within Netflix. So the way software is currently written in Netflix and allows maximum freedom for microservice owners is for owners to decide when they can migrate to a new version of software or hardware or architecture. So eventually we'll be in an ecosystem where there are some clients that already have IPv6 addresses, but the servers that they're connecting to are still on IPv4. This could be due to various reasons, such as the IPv4 address servers could in turn be accessing other IPv4 external upstream dependencies, and they might in turn be exercising freedom on when to move towards IPv6. So in this hybrid form of network addresses, we need a translation mechanism whenever an IPv6 address client is trying to access an IPv4 address server. So the current state of the art, of course, is to use network address translation, either in its software form or in hardware. And both of these approaches suffer from a common problem, that is, each one of them suffer from per packet latency, because we're trying to perform that kind of translation from v6 to v4 on a per packet basis. So we began examining if there's a more optimal way of performing a network address translation function within our ecosystem. And of course, the solution is to use TSA. TSA stands for the Titus syscall agent. It was primarily written for Titus, which is Netflix's multi-tenant container platform. It is a container orchestration platform using which we launch hundreds of thousands of containers every day. So essentially, the Titus syscall agent uses a kernel mechanism to intercept system calls. And through the rest of this presentation, we'll look at how this interception works, how the TSA has been architected, a live demo of the TSA working, and we'll talk about a little bit about the future problems and opportunities, and we can take questions after that. So how does TSA syscall interception work? So there are many existing approaches to syscall interception. What's required and what's new is what we got from seccomp. So seccomp is a powerful way of intercepting system calls. And recently there have been changes where seccomp can notify a monitoring process of changes of whenever a system call is issued. And within that system call, you can add and swap FDs, file descriptors, and these have been changes that have been introduced in the past few years. So Sargan, our former colleague, was instrumental in adding the last support to swap file descriptors from within the operation or interception of a system call. And that is what we use within our mechanism to implement the network address translation function. All right, so let's look at a sequence diagram to understand the TSA architecture in more detail. So Titus, again, is our container orchestration platform. And when it starts initializing a container, the Titus creates a seccomp policy filter. The seccomp policy filter is a combination of system calls that Titus wishes the container to handle, and then this handling is in turn done by a separate TSA sidecar that's running for each container. So the seccomp policy is installed with the kernel. The kernel returns a notification file descriptor, again a change added in 2017. This notification file descriptor is sent to TSA, and TSA from then on begins monitoring changes, or rather notifications, to that file descriptor. And each notification is a notification that the container which gets launched with the seccomp policy makes a system call. So whenever a system call is made that matches that filter, the TSA gets triggered, and TSA in turn will examine the system call and then will try to extract system call details. And the magic here is that TSA, of course, is launched with elevated privileges, wherein it can perform operations that the container cannot perform, and it can lead to a better outcome for that particular system call. So the system call is then executed in the context of TSA, and the results are returned to the kernel, which pipes those results back to the container, which originally issued that system call. So this is how the TSA has been architected. Let's see how this maps to the network address translation function. Over the next few slides, we will see the interaction between a client and server in various combinations of IPv4 and IPv6. In this instance, we have a IPv6 client that is a container, and it's trying to initiate a connection to an IPv6 server. So the TSA is already running in the system, and it's meant to intercept every network system call. Now, there is a IPv4 bubble that you see within TSA, and that's because when the Titus agent starts up, it creates a separate network namespace with an IPv4 address in it. So in this instance, when the container makes a connect system call, the connect system, what we do is we check this system call and we look at the connection details, and we figure out that the destination is in fact an IPv6 destination. So in this case, we don't have to perform a network address translation function. So what we do is we do a pass-through of that system call to the kernel, and the kernel in turn returns the file descriptor, which is the return value of the connect, directly to the IPv6 container. And from then on, the interaction with the server is complete, and the TSA and the kernel is not in picture. Now let's look at a situation where TSA is not in the picture, and the IPv6 enabled container is trying to connect to an IPv4 service. So without TSA in the picture, no seccomp policy is installed, the connect system call goes directly to the kernel. The kernel in turn returns an error that it cannot reach the server because the server is an IPv4 server. So this is the situation that we want to remedy with TSA. And let's see how we do that. Now the same situation, but with TSA, where we have IPv6 enabled container running on Titus agent with the TSA process. It's trying to connect to an IPv4 server. The connect system call comes in, and TSA intercepts it because we had a filter for connect in the seccomp policy. And then we look at the internals of the connect system call, and then we figure out that we're trying to connect to an IPv4 address. We check if we have a route to that IPv4 address, and once we figure out that we do, we change to the network namespace that has an IPv4 address. So we want to enable this connection between an IPv4 address, a client, and an IPv4 server. So we swap our network namespace to move to a namespace that has the IPv4 client address. After we do so, The connect system call goes through because the server is also IPv4. We get a return value of a file descriptor. And what we do is we use that file descriptor to mutate the original file descriptor that would have been returned by the kernel when the IPv6 container did a connect system call. And we use the add FD functionality that was part of the kernel feature in 2020 that Sargon from our team added to perform this swap. So what this enables is from then on, the network transaction is directly between the container and the server with no packets of that transaction being intercepted by the kernel or TSA. So we avoid the per packet processing. At the same time, we're also achieving the network address translation function. So that much for the slides. Now we'll have a live demo of this through Alok. Alok?
Thanks, Keerti, for the presentation. So I'll be showing how we use Titus seccomp agent to make connections to a v4 dependency when your application is running in a v6 only network mode. So let's say you have an application, you want to migrate it to a v6 only network. And what happens is your certain dependencies might not be ready and they might not be ready to move to a v6 only environment. So I'll be showing how connections to a v4 dependency would work on a container that's, let's say, running only a v6 network. So here, as an example, I have a container that's moved to IPv6 only. So let's look at its network. So what we see here is we have an interface which has an IPv6 address only. So now let's see what happens if we connect to an IPv6 destination. So I'll be using ifconfig.io as a dependency for my app to connect to. Let's see what happens when we connect to using a v6 address. So we see that we are successfully able to connect to the v6 address. So now let's try to do this with a v4 option. As expected, what happens is when we try to connect to a v4 address, the connection fails with network is unreachable error. Now let's see how TSA helps solve this problem. I'll move to a different container which is running v6 but with TSA. Again, we'll examine the network of this container to confirm it's still a v6 address. Obviously, a connection to a v6 destination should just work fine. So it does. So we are able to connect to the v6 address successfully. So now, just to show you how TSA intercepts the system calls and how it's able to connect to a v4 address, I'll show you a screen which is the host for the container. So this is the container host. If you look at the network setup here, if we run ifconfig, what we have is a v4 address. So this is a separate network namespace that we create, and the containers use this network namespace to connect to a v4 destination when TSA intercepts their network system calls. So to show that it's indeed intercepting the system calls and connecting to the v4 address, I'll run a TCP dump to show the connection to the destination, which is ifconfig.io. Then also in another window, I'll just show you the logs for the Titus syscall agent itself. So here I'll be running the log and grepping for the destination IP addresses. So now if I go back to the container, which is using TSA, and if I try to connect to a v4 address, so we see this connection was successful. It was able to successfully connect to a v4 destination, even though the local network is v6 only. If you look at the TCP dump for this, we see that the transition network namespace IP address was used to make the connection. So the source IP would be the IP address of the transition namespace. And we see that it's able to connect to the destination using a v4 address. Similarly, on the log side, we see that the TSA handled the network connect call, and it was able to connect to this destination and thus enabling the container to connect to a v4 dependency with its v6 address only. So this shows how we are able to intercept system calls, specifically the network ones, which enables us to connect to, let's say, a v4 dependency when using a v6 only container. And to add on to this, what we see here is the TSA is only handling like system calls. It's not like changing every packet's address as what could happen in a system using something like a NAT. So this is more efficient. The TSA just intercepts the system calls and gets out of the way. That's it for the demo for TSA. I'll hand it off to Keerti for the rest of the presentation. Thank you.
Thanks, Alok, for that presentation. So once again, we saw a connection between a v6 client to a v4 server go through without doing per packet processing and achieving the network address translation function. So as with all teams within Netflix, when we made the TSA operational across thousands of Titus agents, we have operational dashboards that tell us crucial information as to how many containers are being launched with TSA, what are the different system calls that are being intercepted, and their latencies. A word over the future. While implementing TSA, we encountered multiple issues. The most serious one amongst them all was something that Alok wrote to the kernel mailing list, and it has to do with the handling of the epoll file descriptor within the add FD feature of seccomp. So we hope that a solution for this comes from within the kernel in the next few months. To mitigate this particular issue, we implemented a kernel module that maintains the complete life cycle of the socket. So along with TSA and the kernel module, we take over the complete control of when sockets are created from in the kernel whenever network system calls are being intercepted. So TSA will achieve this network address translation function and will be used in the short term and will be on by default within Netflix. In the long term, once we've achieved a complete migration to IPv6, we might not require TSA in its form to achieve NAT. But TSA can provide other valuable support by intercepting system calls related to both perf tools and BPF tools because of its advanced system call interception capability. That's all for the presentation today. Thank you, and we are ready to take questions.